Okay, so stream should be live. Let's get to it. How's everybody doing this morning? Good. Oh, I need to change the. This is really annoying that I have to do this. Oh, it does help if I plug the cable into the iPad. Derp. Okay, there we go. So last time we talked about surface area, and we used Gabriel's horn as one of our examples. Oh, and the projectors aren't even on. Sorry, guys, I'm not really with it yet this morning, am I? Okay, so today we wanted to do basically, well, what was the warm up about? Yes, it was a lot of work, right? Huh? Yeah. Failure. Yeah. All right, well, let's go back through the idea here. So if I want to, let's say that I have a pulley and a rope and a mass on it. And let's say that the distance is d, okay? Then how much work does it take for me to lift the mass a distance d? Okay, right. So this is the assumption, right? Is assume that the rope weighs nothing, it's magic, and that the pulley is like perfectly frictionless. And furthermore, that this mass, like I've drawn it as a box here, but it's like it's all concentrated at a point, right? Yeah, exactly. Well, that's what we're doing today. We're doing physics class. So maybe what I should have done is gotten on my best Dr. Brown costume and, um, come in and talk about, well, an excellent student would. Is anybody in physics right now with Dr. Brown? Or no, it's Dr. Kraus, right? Um, yeah. Well, okay. Anyway, so yeah, we're gonna make a bunch of those sort of standard physics assumptions, such as assume a spherical cow, and um, yeah. All right. So how much work does it take to do this? Well, what is the definition of work? Right. Okay. And so, what is the uh, work, or what is the force that's necessary, or maybe better put, this relates to the mass, right? Because how is the force and the mass related? They're directly proportional, and what's the constant of proportionality? Okay, and so what's the acceleration? The gravity, right? So in this case, if I think about this in metric units, where I'm thinking about it as a mass rather than a weight, then I'd need to multiply by the 9.8, right? Basically to get the weight. Okay, um, so if the mass is in kilograms, say, then the force would be 9.8 times the mass. Uh, well, okay, good question. So gravity points which way? Okay, so if I make that the negative direction, then the weight of the object would just be 9.8 times it, right? Because weight is a dimensionless quantity. But the other reason that I want to write it as positive here is, well, gravity's pulling down, but which way am I pulling? I'm pulling up. Well, okay, if there's a pulley, but right? Like I'm raising the weight. So the force that I'm applying is going upwards. Okay. Um, okay. And so it would be that if we were working in metric units, but if we're working in imperial units, uh, then we tend to state things in terms of their weight rather than their mass because America. Okay. Um, so the sheet for today, Dr. Insaldi and I were sort of joking yesterday. She came down and said, "I've got it. I've written the sheet, but I'm sorry I didn't change everything from foot pounds to kilograms." And I was like, "That's okay," because I she knows I hate the imperial unit system. I think it's stupid. Right. So anyway, but yet we still use it. Uh, well, okay. Liquid measures in the imperial system, if you use all of the terms, are actually pretty clutch because everything's a power of two instead of a power of 10, right? So there's two thises and a that, there's two pints in a quart, there's two quarts in a something, there's two of those somethings in a gallon. Well, yeah, exactly. That's the problem, right? We don't use and remember all of those terms anymore. Um, And if we did, right, it actually kind of makes sense. Um, yeah, but like there was a special word for half gallon or like half of a pint. So it would be what 8 ounces? Well, that's a cup, right? But then there was what's half a cup? 4 ounces? I don't know, but there used to be a special term for that, right? And then half of that would be 2 ounces, which was another special term. Okay, I don't remember what any of these things are, but point being, they went up by powers of two rather than powers of 10, like in the metric system. And at that point, right, well, who really cares? Power of two, power of 10? I mean, Cole and I work in base two all day, right, in computing. Um, why is base 10 maybe preferable? Well, because our arithmetic system is already base 10 and we have 10 fingers. Um, okay, so yeah, that part of the imperial system is kind of handy, but it's sort of archaic still, and the rest of the world doesn't use it. I think that's the real important crux. Okay, so I think that's the only advantage that I can think of. Oh, actually, you know what? The original Fahrenheit scale for temperature was actually kind of that idea. Was that he put 32 as the freezing point and 96 as uh, human body temperature. Okay, but what's the difference between 32 and 96? 64. Yeah, like actually just do the subtraction. Yeah. 64. Well, that's a power of two, which means you can cut that into a bunch of half intervals really easily, right? So anyway, um, okay. So back to our physics problem here, right? So what do we got to do? If I want to raise this mass, then how much work does it require? Well, it's going to be whatever the weight is times the distance, okay? Whatever that is. Okay, what would the units for this be if I was doing it um, in metric? Well, the distance would be, say, in meters. It's not kilograms per meter because I'm multiplying by meters. Well, what's the units of acceleration? Well, yeah, it's like meters per second squared, and then I do so anyway. The whole point is it's Newton meters. Okay, Newton is the unit of force, which is a gravity times a weight, I mean a mass, and then distance would be in meters or whatever. Okay. In imperial units, the weights are usually given in pounds, and the distance is in feet, and so the unit is foot pounds. Okay. Um, anyway, but yeah, that's the same idea. All right, so that is the idea if we're just doing this with a single mass. But what about if this mass is distributed vertically? Then what? Right? So this would almost be like, imagine that I had, like with the rope or the chain, okay? Let's imagine that the chain is d units long and it was like there was a certain weight per unit length. Okay, so say the chain was 5 pounds per foot. Okay, in a sense, that's kind of like almost like a density, right? Because it's the amount of weight per piece of the thing. Okay, so and let's say the distance is, I'm just going to make something up here. Let's say that the distance is 10 feet. Okay, how much does it take for us to lift this whole chain and wrap it around the pulley? Well, what's the trap answer here? Okay, that actually would work, right? Um, I think, right? Which is, so Cole's suggestion was to think about the center of mass, right? So in this case, I would have 50 pounds worth of chain, and I could think of it, well, it's basically distributed, right? Since if it's uniform length, then I could think of that thing as being in the middle. And so let's actually work out what it should be and then see if it comes out to be that exact amount, as just thinking of it as a point mass at the center of mass. Okay. All right. So here's the idea. How much work does it take to move the chain that's already at the pulley to lift the very, very top link of the chain? Nothing, because it's already where it needs to be. Okay. How much does it take to do the very bottom length of the chain? Well, it'd be whatever the weight of the bottom length is times the 10-foot distance. Okay. And so if I think about the chain as being a bunch of little tiny links, then what am I doing? I'm calculating the weight of each length times the distance that each length needs to travel. Well, does that kind of clue us into something? Yeah, that would be an estimate, right? Because if I say there's 100 links along this chain, each one's really tiny, and I do the computation for each chain for each link, and I add them all up, then that gets me an estimate of the total, right? Does that seem reasonable? Okay, now you guys can't see my evil grin underneath my mask, but where are we going to take this? Integrals, chop it up to finer, right? So what happens if I slice it up into a bunch of millimeter lengths? Yeah, I get closer and closer. Okay, so what I'm going to do is that the total work, okay, is going to be the integral of force times distance, right? It's just that we're summing up, or in the case of the integral, right? The integral is really the limit of a sum, right? And so in this case, what will we have? Well, we'd have, what is the force? Well, um, it's 5 pounds per foot times a chunk, okay? How long is a link? dy, right? Okay, so that's sort of the weight of a little piece of it. And then we need to multiply by the distance. Well, how far does the link, let's say, y units uh, below here need to go? Needs to go y units, okay? Okay, and then what are the bounds of my integral? I would need to go from, well, it depends on how I set up my coordinates here, but I would say I'd probably want to go from -10 to 0. Um, no, it's not that it's gone, it's that it's built into the concept of a pound, right? Because before, when I was doing this as a point mass, the emphasis word there is mass, not weight, right? So And then, of course, what's the relationship? Well, weight or force is mass times acceleration. If I give this in imperial units, in pounds, the gravity is already assumed to be part of it, right? This is the other reason that imperial unit, well, one of many reasons that an imperial units are stupid is because they're Earth centric, right? The concept of a pound um, only exists on the surface of the Earth. If we suddenly find ourselves on the surface of Mars, you haven't done that yet? Oh, that's too bad. Or the moon, right? The pound is not the pound. Mhm. No, they weigh you on a thing and then divide by 9.8, right? So that you know the mass, right? Well, or you use a balance with a, yeah, well, that works. Oh, no, I don't actually. But that is an interesting question. You can't put yourself on a scale if there's no gravity. So, um, yeah. Okay. Anyway, so what is it that we get when we do this? Well, 5y dy integrates to what? 5y squared over 2 from -10 to 0. Okay, of course, plug in 0. What do you get? Nothing, right? That makes sense. Plug in 10. What do you get? 100 over 2 is 50 times, so it would be 250. And technically, it's negative here because I messed up the coordinate system. What? Um, well, let me look then because there's a reason I don't teach physics. And that's because I'm incompetent. No, that's right. No, because it was 50 pounds per foot. Hmm? Yeah, so in this case, it's 5 times, right? Okay, there are three terms, right? There's this, and there's that. Okay, y is the distance that we need to move a piece, and how much does each piece weigh? Well, it's how long is it? It's dy. How much is it weight? Its weight per unit length. It was 5 or whatever. Okay, so I should have done this from 0 to 10, but okay, so what really should we have? 250 foot-pounds. Yeah, right. Well, okay, because right, the work is um, work. I suppose we could associate a direction with this because, like, if it takes me 250 foot-pounds of work to lift the chain, how much work would it take for me to drop the chain back to where it was? Well, okay. How much would it take me? None. But how much would it take the Earth? 250, right? Okay, so I can think of work as being positive, negative in the sense that, like, maybe here's a better example. If I walk up the stairs, I'm doing a lot of work, right? Because I'm massive, too massive, and I'm hiking all the way up some distance, right? But if I come back down the stairs, work is still being done. It's just not being done by me. Now it's being done by the Earth, okay, which gets hot and sweaty uh, because it's massive. No, I'm kidding. Okay. Um, yeah. All right. So does that kind of make sense? What we're just integrating here is piece of force times distance, right? Gucci? And then we get whatever we get. Um, okay. So would we have gotten the same number if we thought of this as a center of mass thing? Okay. Actually, yes, because what's the total weight of the chain if it's 5 pounds per foot and 10 feet? 50 pounds, right? And where would the center of mass be? Well, I would assume it'd be halfway, right? Okay, so if we've got 50 pounds that we need to move 5 feet, how much work does that take? 250 foot-pounds, 50 times 5. Okay, congratulations, you just discovered the mean value theorem. Okay, anyway, so yes, I guess you could do that. But here's the thing though. Why did that work? Because it was pretty easy to compute the center of mass of this thing because it was a uniform distribution of weight. Well, what about if we had some really weird chain that got heavier the further down it went? Like it got thicker the further down it went. Well, it'd be a really weird and possibly terrible chain, but who knows, right? Okay. All right. So, anyway, all right. So let me go back over here. Oh, and I need to switch the power over to this thing so it doesn't die. We've done that once too many times. And then, of course, it doesn't like to work. I am so getting ready to defenestrate this laptop. Okay, so let's keep going. So let's take another problem here. Okay, so let's say that we've got a 50-foot distance. Could we combine these ideas? I guess is part of the issue here, right? So what about if I have a 300-pound bucket? Okay, so this will be 300 pounds, and then I have 50 feet. Huh? Oh, because it's on OBS on that. Yeah, so it's going to be delayed on the right-hand screen. Let me actually um, switch this over. That's probably a little easier for you guys to see. Okay, so 50 is the length, and then the weight of the rope is 4 pounds per foot, and we want to raise this thing up 20 feet. Okay. So in this case, we don't want to raise this. I guess would be the other reason to not necessarily do the center of mass version. Um, okay, because in the previous problem, we went ahead and raised this thing up by exactly the length, right? Well, nobody said I had to do that. I could have raised this by, any quantity. Okay. All right. So what are the two pieces that we've got here? If we were just going to raise the chain or the rope, do we know how to do that computation? Okay, it'd be an integral, right? What about the bucket of cement that's at the bottom? Okay, could we split this and think of the two as separate? Uh, okay, think about that though for a minute. I'm not saying we have to, I'm just asking, could we? Okay, okay, so Cole suggests to treat one as a weightless rope. So I claim that you can't treat them separately, and here's why. If we did, that would be like raising a rope and then separately raising a 300-pound weight. Okay? What's the problem with that, though? Huh? You don't see a problem? I do.
Well, if you're just raising the chain, then you're having like that weight, and then if you have the weightless rope, then you're raising that log.
Okay. But how much force? Yeah. Right. Well, let's find out. Right. Let's do it both ways. Let's think of them as being combined, and let's think of them as being separate. Okay. So let's do the separate case first. This thing is still not wanting to charge. All right. Well, whatever. Let me get my other charger. Okay, so think of it as a separate situation and work it out real quick. Okay, so how much work would it require to raise the 300-pound bucket 20 feet? 6,000 foot-pounds, right? That part's easy. All right, what about the chain if we disregard the existence of that 300-pound bucket? How much work would that take? What would we be integrating? We'd be integrating what? 20 times, or not 20, 4 times what?
Wait, are we raising it 20 feet for both?
Yes, yes. Good.
So
No,
your
good
distance is
question.
20?
Huh?
Is
Yeah, your distance is 20. Okay, and um, but that's right. The distance, right, is the bound of the integral. Okay, so how much do we raise? Um, let me start sketching here once I get the laptop from dying. Okay, there it goes. I don't know why the old laptop doesn't like the new charger, but whatever. Okay, so where were we? Where's my pencil? Huh? Oh, it's on the table. Okay, thank you. All right, so the easy part was the bucket, right? So the bucket, it's 300 pounds times 20 feet, 6,000 foot-pounds. Okay. All right, what about the chain? Well, how far am I raising a given quantity of chain? Well, okay, what's the density? It's 4 times dy. How much am I raising a given quantity? I'm raising it by y units. Okay. Um, and then what are my bounds here? How much am I raising the thing by? I guess it'd be what, 0 to 20? Yeah. Okay, so what do we get if we do that? Well, it'd be 4y squared over 2, so 2y squared from 0 to 20 would give us what, 400, 800 foot-pounds?
Why is it 40 wide?
Because the dy is the height, right? The length of an infinitesimal piece, and it was 4 pounds per unit length, right? So the 4 was the density, yes. So the 4 foot-pounds is 4 by itself, right? But what am I doing? Or sorry, not foot-pounds. It's pounds per foot. But dy is in feet, so when I multiply those, what do I get? Just pounds. and then the y that's in the front there is a distance, so that when I total this all up, I'm getting, well, exactly foot-pounds. Okay.
I need you to know that this is not how she did it on the warm-up.
It isn't?
No. It worked on the first one because it was the full length, so it was half and half. How she did it is she calculated the force as a function. So she took the full weight minus the change in weight, and then the infinitesimal was the distance, the dy.
Okay, so am I being a complete moron today?
Well, because 800 pounds seems a bit small for, or feet pounds seems a bit small.
Well, okay.
And if you calculate the full distance, you'll get the right answer doing what you're doing, because
Right.
it'll just split it in half.
Okay, so I'm being incompetent is what you're saying.
This is just not how the warm-up did it,
Okay.
and I'm afraid that it won't work for distances that aren't the full length of the chain.
Okay, fair point. Well, let's go through and rethink it then.
She would calculate, or she calculated force as a function of y. So she took the full force, full length, which is in this case 50.
Okay, so the force is a function of y. Well, first off, I need to choose where am I going to put the origin, the top or the bottom? Let's put it at the top, probably. Okay. All right, so then if I am y units down, then what's the force associated with being y units down? It would be what?
Oh, sorry. You'd have a linear function,
Okay.
and your intercept would be
Okay, I'm now starting to understand the question I got from. I got an email yesterday from somebody asking a question about the warm up, and I looked at his setup and I'm like, what on earth are you doing? It's just this. But it was the full length of the chain. And so now this is starting to make more sense. Okay. Huh? No, I think it's not that we did it wrong. It's just that I probably made an assumption that worked fine in the case of the pulling up the full rope, but isn't going to work here because we're not pulling up the full distance. Okay, so all right. So what's the force um, at height y? I guess is the question, right? Well, okay. At height 0, it's well, okay. We have to choose that, right? Which way did Dr. Insaldi do it?
um,
Well, you know what? Let's not be idiots here. Let's let's just go look at her. Did she post a video?
I think we were saying 0 at the bottom, because we were doing, for this one would be like 200 pounds of chain minus 4y.
Oh, yeah. Okay, okay. So let's do let's put 0 at the bottom.
The force at the top would be 200 pounds.
Okay. And because that's the total weight. Okay. All right. So then what's the total weight? 200 minus 4y. You decrease the amount of stuff. Okay. All right. So that's the force at height y. So we would need to integrate that times dy, right? All right, and so what are we going to get? We'll get 200y minus 2y squared from 0 to 20. And so we'll get 4,000 minus 800, which would be 3,200 foot-pounds. Well, plug in 20, right? Oh, I see. Okay. Um, yeah, okay. So I guess what we calculated a minute ago would be uh, the we calculated the 4y part, right? which is, so we had 800 here, right? But we would need to subtract that because we are, um, yeah, let's think about why that's the case. No, okay, that makes sense. All right, so what's the total then?
92.
It'd be 9,200, right? Well, okay, so because there were two pieces of this, right? We just the 60, huh? No, no, sorry, that's not what I meant. Uh, if it was just the rope we were pulling, it would take 3,200 foot-pounds. That's what we just calculated. Okay. If we just had the bucket with magic rope that didn't weigh anything, moving the bucket required 6,000 foot-pounds, right? So if we add the two, then it should be that. Okay. Um, yeah. Okay. Does that kind of make sense? 200 here is how long is the rope? 50 feet times how much does it weigh per unit length? Okay. So that's the total weight of the rope was 200. And then the um, the force that you have to apply, right? Okay, so maybe here's a way to think about it. How much force do you have to apply to move the bottom part? Well, you've got to apply 200 foot-pounds because, um, or pounds rather, because you've got the whole weight of the chain, right? But as you move up the chain, or maybe I guess down the chain, however you want to think about it, right? You have less stuff to worry about. Yeah, okay. This is why I hate teaching this section because it's always really hard to explain. Um, bleh. Now I just want to go home and nap. Um, okay, so um, yeah. All right, now let's think about it. What about if we thought about these two things as being combined, right? So, and this is the question, right? Is so when we went into this, we came at it with the perspective of, well, what about if, so we've got a weight that's at the end of a chain and the chain also weighs something, right? How much work does it take to move this whole contraption? Okay. And so we said, all right, there's two ways we could approach it. One would be let's just pretend that we really have two separate processes moving the weight with magic rope that weighs nothing and moving the rope that has nothing at the end of it. And that's where we got 6,000 and 3,200, and then we added those up. Okay. Now, if we reset this up where we genuinely think of the two things as being linked, are we going to get the same number? That's the question, right? Okay, so do we see what the question is? Okay, yeah.
So on the chain one before, why didn't we do 50 minus 5y?
Okay, we should have,
Okay.
but because we went from 0 to 50, it didn't matter.
That's where your negative comes up.
Right.
Why wouldn't it matter then?
Because the bound, well, let's go back over here, right? So we should have done this as what? 50 minus 5y dy from 0 to 10. So this is Will's point. If you plug in 10, oh, yeah, sorry. I was thinking of the next term. Um, So on that one, it just so happened that this and that, this was exactly half of that.
Just like ironically.
No, it's because I was doing the entire length.
So you don't have to technically put the 50 watt.
If you're just doing the entire length.
But if you do that, then you're kind of safe no matter what.
Right, right. Which is Will's point, right? So what we wrote here for the previous one wasn't wrong for that particular problem. Okay, but it's not. It didn't generalize, which is what we saw over here, where for this one, the 4,000 and the 800 were not 50-50, right? Um, yeah. Okay. How long was this rope again? 50 feet, and it was 4.
4.4.
Okay. Um,
So what do you?
huh. Although I guess is no, never mind. Okay, go ahead.
Correct. What do you like? What is that? So after y to 4y, what are those things? Like, what are those variables?
Okay, so good question, right? So where did the 200 come from?
50 times 4.
Right, which was the total weight of the entire chain. Okay, what was the 4? 4 pounds per foot. Okay, and then y was a number of feet. Yeah. Well, okay. So let's maybe think of it this way. For just a little bit at the bottom, okay, it takes a lot more work to move the thing at the bottom than it does something at the top. So how much force is required to move the bit of chain at the very bottom? 200 pounds, because you have to move the whole bloody chain, right? How much force is required at the very top of the chain? Well, basically nothing, right? Because, well, it's already there. So the amount of force required for a little chunk, a little piece of it decreases as you move up the chain, right? And if it's full at the bottom and none at the top, well, then 200 minus 4y does the job, because if y is 50, which would be the entire length, then what do we get? 0. And that makes sense, right? The little bit at the very top of the chain requires no work. I've really botched today. I'm sorry, guys. I'm a horrible professor and deserve death. Um, okay. And Coy is probably like online here, like, where did we get 200? Yeah, Farden. Uh, I'm being a bad professor today. Um, don't tell Dr. Brown, because he'll come down to my office and mock me. Okay. Um, okay. So, yeah. All right. So, what would be the question if we tried to combine these things? Well, how much force would be required if we also considered the mass, the 300, as part of this? Okay, so if I thought of f of y as being how much force does it require if I attach the bucket to the chain? Well, I still have, that's the amount of force it takes just to move the chain, but how much is the bucket? It's 300 pounds, right? So I claim that we just add this. Okay. All right, now if that's f of y and I integrate f of y from 0 to 20, then this would be the same as doing, oops, aren't those the same? Can't I split the integral? Yeah. Okay. And that's a good thing because that second pair, like the two split integrals, that's basically what we did a minute ago, right? So what's the value of the first integral? This guy here. This was the 3200. And what's the value of that second one? It's 6,000. Okay, that one's easy. Okay, so what's the moral of the story? Could we split these things up? Yeah, we could. Okay. Um, Now the next example that which we won't really finish is a little bit more complicated, but you know what? What I think I should probably do is make a supplementary video after I come up with a better way to explain this, and then yeah, because I don't think I've done a very good job today. Um, okay. Anyway, well, because the next example throws in a really interesting wrinkle. But yeah, go ahead, Jack. Hmm. Yeah, it'd be like and this is kind of what I was trying to get at with the thinking about it in terms of like each individual link, right? So each individual link has a force required, and it also has to go some distance, right? And so I'm thinking of the dy as being like each length, and then the thing that goes next to it is the force required for that length, and then I'm totaling it up, right? Which is essentially an integral, right? So if I imagine taking a rope and splitting it into 100 sections, right, then I would have a delta y, right, which would be 1/100th of the total length or whatever, right? And then what's the whole idea but to go from a sum to an integral with a limit as the width of those things goes to zero, or equivalently, the number of them goes to infinity, right? So, uh, yeah, I mean that's why we're integrating, right? Is that we really are taking a limit here. We're just kind of sweeping it under the rug because you guys are big boys now. Okay. All right. So the next example, which I'll work through and come up with a good way to explain it, is kind of evil. So here we were lifting a 300 bucket pound of or 300 bucket pound of concrete, a 300-pound bucket of concrete. Get the words in the right order. The next example is kind of evil. She said, okay, now let's imagine that we're raising a cube of ice. Okay. And the size of the thing is whatever. Okay. And the rope is some weight per unit, and we're raising this how much? Okay. If we were doing this in Alaska, well, maybe not today. If we were doing this in Antarctica and we started raising this block of ice, do we have to worry about the ice melting? We're all good, right? We don't. But what happens if we do this outside today? Well, the ice is going to start melting as we're heaving on the rope to lift it up. Well, as it melts, what happens? The weight of the ice block decreases. Okay? So if we start lifting and we're like, let's say we're going real slow because it's heavy lifting, right? And an hour later we're still lifting. Well, the amount of weight that I have to worry about an hour from now is not the same as right now because some of that ice is melted away. Yeah, she gives an assumption for sort of the rate at which it's melting, right? Which is we'd have to factor that in, right? Because it uh, I don't think it would realistically be a constant, right? Because we'd have to think about the surface area and whatnot. But let's just assume it's like, maybe a better way to put it is, imagine that it's just a big bucket of water and there's a leak in it, right? So it's leaking at a constant rate.
Can you do mean value theorem?
Probably, but I think what Will's point though was that mean value theorem was just lucked out to be exactly halfway last time.
Or if it's constantly moving?
No, I don't think so. I think we have to, yeah, yeah. Anyway, all right. Well, I'll post some supplementary stuff from this because I've been or actually, what I had to do was just bribe Dr. Brown to do it, and then we'd be better. So, okay. All right. Well, we'll quit for today. Um, yeah, Cardinal, it's going to melt, and yeah, we'd have to do some differentiation business to figure out rates of change. But I haven't actually stated formally the problem, but that's sort of the idea that we'll have to deal with. So, all right, we'll quit for today, and I'll see you guys Friday, hopefully with more competency.